Ecliptic Etude is an audiovisual work in which the movement of the planets is presented. Basically, there are two ways of converting visual motion into sound or vice versa. One is realization, and the other one is abstraction. Realization is the scientific approach based on accurate measuring, preliminary research focusing on mathematics, which is the common language between science, fine arts, and music. On the other hand, abstraction is rather an artistic attitude with free associations and the enhancement of essential features and characters. In fact, both of these two methods are simultaneously present in transformative artworks. For instance, much as one tries to insist on exact physics and mathematics, there's always a critical point where some numeric values have to be modified erratically, or else the final result would be uninterpretable because of the boundaries of human perception, so henceforth realization techniques are more or less mixed with abstraction. In Ecliptic Etude, I associated the orbit length of planets with the frequency range of human hearing, as well as the orbital period with pitch oscillation time of a sine wave. The implementation process will be detailed hereunder. Human audio spectrum ranges from 20 to 20,000 Hz. Although it is a relatively large scale, we cannot differentiate between the higher frequencies as exactly as between the lower ones because our hearing is nonlinear. To solve this problem, it would have been a logical step to transform the planetary movement to a logarithmic scale, but in this case the orbital speed of the planets would have been extremely fluctuant, which is far from reality. Instead, I rather kept the linear system and chose frequency values that are easily distinguishable. First, I set the two extremes, Neptune and Mercury. The orbital length of Neptune is almost 80 times longer than Mercury's. It is an enormous difference. Therefore, I had to apply a multiplier value by which Mercury's short track assigns a frequency range that is large enough for our ears to clearly perceive the changes of the pitch, while Neptune's long track results in an interval whose highest value is still definable as a root note, not only as an overtone. The most suitable multiplier number I found is 40. The reason is simple. The common unit for measuring vast distances in the solar system is AU. This is the abbreviation for astronomical unit. Neptune's complete orbit length is 188 and 925 thousandths AU. If I multiply this number by 40, the result will be 7,557. Sine waves around 6 or 7 kHz still can be perceived as single musical notes without special amplification, so this amount is appropriate. The next step was to determine the lowest value. I chose 70 Hz because this root note is clearly audible in most equipments without using subwoofer. Then I calculated the total of 70 and 7,557, which is 7,627. This is the highest frequency of Neptune's track. As for Mercury, 2 and 406 thousandths AU is the amount that was multiplied by 40. The product is 96 and 24 hundredths. Then I freely chose a value for the lowest frequency, which is 332 and 88 hundredths Hz, and hereby I defined 429 and 12 hundredths Hz as the highest value. In music theory, this interval is almost a perfect fourth, which I found large enough to have at least 4 well-distinguishable root notes. One may ask, why did I separate notes with constant pitch instead of using these frequency ranges as a glissando circulation? Well, this is the point where scientific realization meets artistic abstraction, and here comes my individual concept. I wanted to present these circulations as musical sequence loops, so I abstracted 4 single notes from each planet's frequency interval. 4 is such a number with which a simple circulation process still can be displayed well. 1 lowest point, 2 rising, 3 highest point, 4 falling. The next operation was to transform the speed of planets into this musical adaptation. The common measure unit for orbital period is day. In the case of the Earth, this number is 365 and 256 thousandths. This is the time interval in which the planet takes a complete circle around the Sun. I simply changed the unit from day to milliseconds without converting the numeric value, so the result is 365 and 256 thousandths milliseconds. Then I applied the above-mentioned 4 divisions, by which the orbital period was divided by 4 in order to get the time measure, or in other words, the beat. In Initially, I endeavored to avoid complicated musical texture, that's why I applied pure sine waves. Then I changed my mind and decided to make the final sound a bit more colorful by using frequency modulation. This synthesis technique then became organic part of the realization process the following way. The interval of modulation index assigned by its lowest and highest value is exactly the same as the numeric scale defining the orbit length of the given planet. Moreover, the modulation frequency corresponds to the value that determines the speed of the planet, or in other words, the orbital period. I applied them without rescaling. Using FM synthesis by this way helped to compensate the lack of the sense of continuous circulation, which is the unwanted result of abstracting static points from the continuous undivided cycle. Yet there's another great tool that helped to enhance the sense of continuity: dynamic spatialization. For the sake of compatibility, Ecliptic Etude is calibrated to a simple stereo system. In spite of the constraint, I tried to utilize this potential as far as possible. The application method was the same as in the case of FM synthesis. Spatial shift is related to orbit length, and the velocity of movement is associated with orbital period. So far I've talked about the musical aspect of my work. Now let's see the visual display of planetary motion. So as to avoid misconception and deceptive representation of the movement of celestial bodies, I did not make such animation in which there are different globe-shaped objects running among elliptical tracks. Although the visual is composed of spheres, it is just a symbolic illusion. These spheres are portrayed as wireframe objects arbitrarily positioned on the screen. The line density of their wireframe is continuously changing. This process results in a periodic pulsation determined by the numeric value of orbital period. Another association is between the frequency modulation and the axial rotation of the sphere, but this modifier factor is not persistently present in my composition. I intended to apply it as an extra feature that makes the visual appearance more attractive, but only at certain points of the work.